Good afternoon, I'm Stefano Bracchi, and in the second webinar of the series, we are going to talk about problem of survey and knowledge of existing masonry buildings. So in the first webinar, last time you've seen this slide, which is representing how Eurocode 8 Part 3 is approaching the problem of the assessment of existing masonry buildings. Now, the first stage is consists in getting the knowledge in having the knowledge of the building current state. In the second step, you have to perform an analysis of the building. It can be a local analysis and or a global analysis. As a last step, you can perform the design of the retrofit interventions. So before looking at what Eurocode 8 is saying, I just want to point out why it is important to get knowledge of masonry buildings, and so why it is important to have a proper survey of the building. It is important because differently from other building typologies, the seismic behavior of masonry buildings is influenced by really a large amount of quantities and of factors. For example, it is influenced by the pattern, quality, and strength of masonry. In particular, it is influenced by materials and by the interlocking between the materials and among the leaves, in case of masonry made by more than one leaf. It is influenced also by the load transfer to foundations, which is a function of the geometry, of the plan or elevation irregularity, the distribution of the vertical loads, and also it is a function of the truss of horizontal elements like roofs, arches, or walls. The behavior is also influenced by the efficiency of connection among the elements, such as the interlocking among walls or the wall-to-diaphragm connections. And it is influenced also by the effect of strengthening elements, such as tie rods or ring beams, that can be present. Finally, it is influenced also by the interaction with adjacent buildings. So the aim of the survey part of the assessment is to get possibly knowledge of all these aspects, because these aspects can be potential weaknesses in the behavior of the building, and can also lead to damage during an earthquake. Now here you can see some example of damages during an earthquake due to these factors that I was mentioning. For example, on the left you can see some collapses due to disgregation of masonry, which is not made by, which is not good quality. On the right, you can see some collapses due to instability of walls, which are made of double leaves, having poor connection. Here you can see some effects, some failures due to problem of plan or elevation irregularity. For example, here you can see a collapse of the facade due to plan irregularity, because in this portion of the building there was a big room, so no transversal walls, which could potentially act as a restraint of this facade. Here you can see some damages due to elevation irregularity. Now, in these slides you can see some example of local out of plane collapses, so collapses due to this kind of mechanism. Whereas on the right you can see the effect of possible horizontal thrusts. Here you can see some essentially collapse, because this is almost a collapse of a portion of masonry. Now, usually these are the mechanisms that are more commonly taking place in masonry buildings. Here you can see some example of global response of a masonry building with only in-plane damage of piers and spandrels. Now this is the most favorable mechanism for a building that an engineer has to somehow to seek. Now how the Eurocode 8 is facing the problem of survey and knowledge. First of all, the Eurocode which is facing this problem is the Eurocode 8 part 3, so which is the part of Eurocode devoted to assessment and retrofit of buildings. Now the current version is the one of 2005, which consists of 90 pages, which can be a lot, but actually is not. Because 90 pages are not only relative to masonry buildings, but are relative to all the structural typologies. Now this code is actually under review, and it is very, very likely that there will be, first of all, a larger amount of information. So probably the new Eurocode will not consist of only 90 pages, but more pages. And there will be aspects taken from other codes, such as the Italian code that has been already updated. The Italian code, which is the version of 2018, but also its commentary, which has been released in 2019. So what Eurocode 8 part 3 is in the current version is saying about this problem. The problem of knowledge and survey is faced in chapter 3. Here, if you look at chapter 3, you can see different sections. The first section regards general information and history. In particular, Eurocode 8 is asking you, or better, asking the engineer to collect information on several aspects. The most important are available documentation regarding that building, that specific building, field investigation, in situ and laboratory tests. It is also stressing, Eurocode 8, the importance of cross-checks between the different sources of information, just to avoid different information from the different sources. Then there is also a section which is called required input data, in which Eurocode 8 is setting a list of information to be collected. These are, I want to stress that these are section relative to all the structural typologies, so not specific only for masonry. Here, Eurocode 8 is asking you to find information regarding the structural system, the dimension of the building, and of the structural elements which are resisting the loads. It's asking you to collect information regarding the mechanical properties of the material, plus a list of other information such as possible material weaknesses, inadequate detailings, and so on. Now, the most important sentence of this part is the last one, which is saying, depending on the amount and quality of information collected, different type of analysis and different values of the confidence factor have to be adopted. Eurocode 8 is then introducing the concept of knowledge level. Well, knowledge level represents simply the amount of information, the amount of knowledge that the engineer is getting on the building to be assessed. There are three possible levels of knowledge, ranging from 1 to 3. KL1 is the limited knowledge level, KL2 is the normal knowledge, and KL3 is the full knowledge. So increasing the number means increasing the knowledge on the building. The factors that are influencing the different knowledge levels are essentially three: geometry, details, and materials. Now, all this information are somehow summarized in this table, which is table 3.1. which I'm going to comment here and in the next slides. Regarding the geometry, of course, the geometry is represented by the geometrical properties of the structural system, of course. Details can include, regarding masonry buildings, especially can include connection between floors and diaphragms, connection between walls and diaphragms, property of joints, and for other structural typologies such as RC buildings, also detailing information regarding the reinforcement. The materials are represented by the mechanical properties of the material of the building. The knowledge level is also somehow controlling the method of analysis to be used. And to a different knowledge level, a different value of confidence factor must be is associated. Now, what is the meaning of knowledge level? The meaning of knowledge level is this one. If you move from KL1 to KL3, you increase the extent of investigation, and so also the cost of investigation, but you reduce the uncertainties. So moving from KL1 to KL3, in theory, you're going to a less conservative assessment. It doesn't mean that you are reducing, moving from KL1 to KL3, that it doesn't mean that you are increasing necessarily the cost, because potentially if you move to KL3, the amount of retrofit that you need can be less. So these are the costs of investigation, not the total cost of the interventions. Now it is the engineer that has to find a balance among all these aspects and select the proper knowledge level. Now let's comment the table 3.1, looking at the different columns. Regarding the geometric survey, Eurocode 8 is introducing 4 definitions. Outline construction drawings. These are documents that can describe the geometry of the structure, allowing for the identification of the structural system, essentially, and the dimension of the different elements. Then it is introducing the detailed construction drawings. These are drawings, essentially are the same as the outline construction drawings, but in addition they have also information regarding details. Then Eurocode 8 is introducing the concept of visual survey. A visual survey is a procedure where the engineer is checking the correspondence between the outline construction drawings to the reality. It's not checking all the elements, but probably, for example, the dimension of the most important elements. Finally, there is the concept of full survey. Full survey is like the visual survey, but is extended to the whole building. And the aim of this survey is to produce structural drawings. So it is used when these kind of drawings are not available, or when you want to reach the full knowledge of the building. Now, regarding the detailed investigation, Eurocode 8 is introducing the concept of simulated design, which consists in considering the code which was in force at the time when the building was constructed, and it consists in reperforming the design according to this code. Now, this is particularly useful for reinforced concrete structures, because in this way you can have an estimate of the amount of reinforcement in case you don't have this kind of information. Then there is the concept of limited in situ inspection. A limited in situ inspection is a procedure for checking the correspondence between the information on the details which are in the documents available and the reality. The extended in situ inspection is essentially like the limited in situ inspection, but it is more extended, and it is used when you don't have information on the details coming from coming from documents, original documents. Finally, Eurocode is introducing the concept of comprehensive in situ inspection, which are like extended in situ inspection, but are, let's say, more extended, let's say. And they are used when you want to reach the highest knowledge level. Now, moving to the material characterization, Eurocode 8 is introducing the concept of destructive and non-destructive test. In particular, Eurocode is saying non-destructive tests have to be used, but also in addition to destructive tests, possibly. There is then the concept of limited in situ testing. This is a procedure to be used when you have information on the material properties coming from standards at the time of construction or from original documents. Extended in situ tests are tests that you have to perform when original design specifications regarding the materials are not available. Comprehensive in situ testing is essentially an experimental campaign like the extended in situ testing, but again, more extended. The difference between the three levels of inspection, limited, extended, or comprehensive, are somehow quantified in this table 3.2. Here you can see that for the different levels of inspection, you are required to check a certain percentage of elements in case of the inspection of details. This percentage is somehow increasing, moving from limited to comprehensive inspections. The same for the material tests. You are required to to test a number of samples per floor, which is increasing from moving from 1 to 3, moving from a limited test inspection to a comprehensive. Eurocode 8 is then introducing the global analysis method to be used in the assessment. It is in particular, it is mentioning linear elastic methods like equivalent lateral forces and model superposition methods, and also nonlinear methods. Finally, it is introducing the concept of confidence factor. Now, confidence factor is a factor that has to be applied to material strength. This factor is reducing when you increase the knowledge. It is used in two ways. It can be used to reduce the strength, the mean strength, when these strengths are used to calculate the capacities, which is almost the largest, the most common situation. But it can be used also to increase the mean strength in case of ductile elements, in case these strengths are used to calculate the demand on brittle elements, and is typically used in a capacity design framework. The values of these confidence factors are, or the recommended values of these confidence factors are listed in this table, and are ranging from 1.35 to 1. Now let's see what Eurocode 8 is requiring the engineer, depending on the amount, depending on the knowledge level that the engineer is selecting. At knowledge level 1, Eurocode 8 is asking you to obtain information regarding the geometry from original outline construction drawings, with also some visual survey. If these original construction drawings are not available, you have to perform a full survey. Now, this part regarding the geometry is essentially common to all the three knowledge levels, so I'm not going to repeat it also for KL2 and KL3. Regarding the inspection of the details, Eurocode 8 is asking you to perform a simulate design, and also to perform limited in situ inspections. Regarding the materials, you have to use some default values in accordance with the standard of the time, even though no indication are given by Eurocode 8 on these default values. And you have to perform also some limited in situ testing. You have to use only linear methods and apply a confidence factor 1.35. In case you select KL2, the inspection of the details, the information regarding the details can be obtained from original construction drawings, although incomplete, also performing a limited in situ inspection. Otherwise, if these drawings are not available, you have to perform extended in situ inspections. Information on the mechanical properties of the materials have to be obtained from original design specification with limited in situ testing, or from extended in situ tests. Differently from KL1, all the methods of analysis, so linear and nonlinear, can be used. And the confidence factor to be used is 1.2. Finally, at KL3, information on the details have to be obtained from original construction drawings with limited in situ inspection, or from a comprehensive in situ inspections. Information on the mechanical properties of the details has to be obtained from original reports with limited in situ testing, or from a comprehensive in situ test campaign. Again, all the analysis methods can be used, and this time the confidence factor is 1. Now this the information that I was discussing before is somehow valid for all the structural typologies. So now the question is there information regarding specific information regarding masonry buildings? Yes, and we have to look at the Annex C of Eurocode 8 Part 3. Here there's a first section regarding general aspects, where the code is asking the engineer to look for information regarding the type of masonry units, the connection between the elements, of course the properties of materials. Regarding the geometric survey, the code is asking the engineer to look for information regarding the size and location of the shear walls that are resisting the seismic load, the dimension of the units, and the location and the dimension of the openings. Now these are quite, let's say, straightforward information. Regarding the investigation of the details, the code is suggesting to check a list of different aspects. The most important are the quality of the mortar, the identification of number of leaves in case the masonry wall is made by more than one leaf. It is asking you to find information regarding the connection between the orthogonal walls and the connection between the walls, the vertical walls, and the horizontal elements, such as floors or roof. Finally, regarding the material characterization, the Eurocode is stressing the importance of non-destructive testing. Here there is also a list of possible non-destructive tests to be performed, which are ultrasonic tests, impact tests, radiography. And it is stressing also the importance of destructive tests, or moderately destructive tests, which should be used as additionally to the non-destructive tests. Possible moderately or destructive tests are flat jack tests, can be used to measure compressive strength or also shear strength, diagonal compression tests, or large-scale tests. Now, we'll try to describe some tests or some, say, procedure to get information on different aspects. First of all, to get information on the geometry and on the details, you can use some non-destructive procedure such as thermography and endoscopy. Thermography consists of using thermal cameras, which is able to find discontinuities in a building. And that's used to see, for example, if there are different masonry typologies in the buildings, if there's degradation of materials, or if voids are present. Endoscopy consists of using, sorry, I forgot the pointer. Endoscopy consists in essentially create a very small hole and put a camera inside so that you can see see portion of the buildings which are not hidden, which are not visible. So you can check voids, you can look possibly at the wall section, floor section, and so you are getting information on both geometry and details. Regarding the material characterization, I've mentioned there are some non-destructive tests which I'm not covering here, and there are moderately destructive tests. One of the most common moderately destructive tests is the flat jack test, in situ flat jack test. It can be performed with a single jack, and in that case you are able to measure only the compressive stress acting on the pier, or it can be performed with two jacks. In that case you are able to measure the elastic modulus and possibly also the compressive strength. How does it work? You are required to perform a cut, an horizontal cut in masonry. If you have a regular masonry, such as this one, you are doing this cut inside the joints. You put a jack inside, and if you have a single jack, you can measure the axial load acting, which is the stress acting on the pier. If you do another cut and you put inside another flat jack, you can somehow control the state of this portion of masonry. So you can increase the axial load acting on this portion of masonry, and somehow you can draw this stress deformation curve. Once you draw this curve, you can get information on the elastic modulus, and if you arrive to increase the axial load up to the failure of this portion of masonry, you can get information on the strength also. The second test is the in situ show test. It is similar to flat jack test, so it's moderately destructive. It is used for regular masonry made of bricks or blocks having weak joints, because the goal of this test is to measure the strength parameters of the joints, so the initial shear strength and the friction coefficient. How does it work? You are required to perform two cuts, and inside each cut you have to put a flat jack test, to put a flat jack. So in this way you can apply an axial load controlling the axial load acting on this portion of masonry. Then you have to remove a couple of bricks adjacent to a central brick. You put an actuator here, and you can apply an horizontal load up to the failure of the joints. So in this way, if you move to a plane shear stress versus axial stress, you can get a point. Varying the axial load and repeating all the tests, you can get different points. So at the end, interpolating the results, you can get information on the initial shear strength and on the friction coefficient. Another test is the in situ diagonal compression test. This is, as you can see from the picture, a quite destructive and invasive test, because you are required to isolate a wall panel, to put a diagonal actuator, which is used to apply a diagonal force. It is used for both for regular masonry, it is used for regular masonry with strong joints, and is used to measure shear stiffness and strength parameters, so tau 0 and G. As I was saying, you apply a diagonal load up to the failure of the panel. Once you know the load corresponding to failure, you then, through simple expressions, you can get information on these parameters. Another test, highly destructive test, is the in situ shear compression test. This can be used for all types of masonry, and again, it can be used to obtain information regarding shear stiffness and strength parameters. How does it work? You have to isolate a panel, apply a vertical load, and then an horizontal force up to the failure of the panel. Again, once you reach the failure, you can get information through simple expressions. You can get information on the strength parameters, depending on the masonry typology, and depending also on the type of failure that you are attaining. The last test that can be used this time is not an in situ test, but it's a laboratory test, and it's called direct shear test. It is moderately destructive because you are required to extract from the building this sample, which is made by 3 bricks and the joints in between. So you extract this sample, you bring it to the laboratory, and you apply an axial force, which is orthogonal to the joints, plus a load which is parallel to the joints. Now, as for the show test, you are able to obtain a point in the plane horizontal stress versus vertical stress, and by varying the force, the axial force, you can get different points. Again, by regression, you can obtain information on Fp0 and the friction coefficient. Now, what I would like to stress here is the fact that not in all the cases, the parameters that you are getting from tests, from in situ tests or from lab tests, are the parameters that you have to use in the analysis, in the structural analysis. For example, if we consider the initial shear strength Fv0, the test that we were mentioning before allows you to obtain information on the strength of the joint. But if you are doing an structural analysis, for example, using equivalent frame approaches such as Tremori, so the Tremori software is doing, you are required to use strength criteria of the elements, which are depending on the shear strength of the panel. Now, these two parameters are not the same. The difference between these two panels is explained in the theory of Mann and Müller. Essentially, the relation between the strength parameters of the panel and the parameters of the joints are represented by these expressions. What I would like to stress is the fact that this expression depends on this tangent of phi parameter, which is the inclination of the crack that can form in a masonry. This inclination can be different if the pattern is different. So at the end, you can have a situation where you have the same masonry with same mechanical parameters, same dimension, same axial load, but the strength can be different depending on the pattern. Now, I would like to talk about some additional issues that are not currently in the version of Eurocode 8, in the current version of Eurocode 8, but will be probably introduced in a future review of the code. Essentially, these are taken from the Italian code, which has been already updated, as I was mentioning before. Now, the first issue regards the reference values of mechanical parameters. Now, if you remember, I was saying that Eurocode 8 is asking you to to use information from standard at the time of construction, but is not giving actually information on these standards. Now the Italian code is doing what is doing the Italian code. What is giving the Italian code is giving interval of variation for mechanical properties for the different masonry typologies. These interval of variation are valid in particular conditions, such as a masonry with weak line mortar, 2 leaves without a good connection, and unstrengthened masonry. So this is the table of the Italian code with the different masonry typologies and the intervals of variation. The Italian code is also stressing the importance of some aspects. For example, if you have a double leaf masonry, the Italian code is posing the attention to the fact that the outer leaf can be very vulnerable. So it's suggesting you to reduce strength and stiffness parameters of the outer leaf if the outer leaf is not well connected to the inner leaf. Now, what do we have to do if masonry is actually has better condition than the reference one? If masonry has better condition, you can still apply the interval variation of the table, but you are required to increase these values using some correction coefficient, which are different depending on, for example, the fact that the mortar has a good quality, or for example, there's presence of recurring courses, or there's a presence of transversal connection elements. Here you can see example of this correction coefficient. You can apply, you see there are essentially 3 types of correction coefficient. You can apply maximum 2 of them using the ones which are giving the largest effect. If masonry has some strengthening interventions, you can again use the same values of the table, but applying another set of correction coefficient. The second issue regards the possibility of updating the knowledge of the material properties based on experimental results. The fact that is that at the highest knowledge level, so at knowledge level 3, you have information on mechanical properties coming from the table that I was discussing before, or from code standard, or from standards, and also information coming from the tests, because you performed some experimental tests. So the idea is to use both the information, to combine the information, and that can be done by a strategy which is called Bayesian updating. How to perform this update? First, you have to define a prior distribution, which is probabilistic distribution defined by the mean and the standard deviation. Both these 2 parameters are functions of these x mean and x max, which are the extreme values of the interval of variation of the table. You are then required to apply these quite simple formulas to obtain the update value of the mean. This formula is a function, of course, of the mean of the initial distribution, of the number n of tests that you performed. It is a function of the average value coming from the test, and it is a function also of this k parameter, which is representing the weight of the prior distribution, so of the information coming from the table with respect to the experimental test. This formula has to apply to each mechanical property. Of course, not to all of them, to the mechanical properties on which you have an experimental information. Well, the code is also pointing out that if you have a large difference between this value and the one coming from the test, but no, the one coming from the prior distribution, you have to somehow, let's say, use this formula consciously. So you have to give a motivation of the use of this formula. Now, with the increase of the number of tests, this final mechanical properties tends to be nearer to the experiment, to the average of the experimental test, because the weight of the experimental tests tend to increase. Well, in this table you can see the values of the k parameter depending on the type, on the typology of test that you are performing, and also depending on the parameter that you are measuring. Now here I would like to show you an example of this updating technique. Now let's consider, let's imagine that we want to update the compressive strength of masonry. We have an information coming from the interval of variation of this property. In this figure, the interval variation of the table is represented by these two vertical blue lines. So these are the extreme of the interval, whereas the mean of the interval, or the central value of the interval, is this one. Now the prior distribution is this blue curve. As you can see, the mean of this, since this is a normal distribution, the mean is the central value of the interval. Then let's assume that we have an average value coming from the test, which is equal to this value, which in the figure is located here. So outside of the interval of variation given by the table. Now applying the Bayesian updating with a number of tests equal to 1, we can obtain a final distribution, which is the yellow one, or say the orange one. You can see that if you are looking at the mean value of this normal distribution, this mean value is shifted towards the average value coming from the experimental test. And this is, say, the aim of this updating procedure. If you increase the number of tests, for example, you move from 1 to 3 or also to 6, you can see that the distribution tends to shift more towards the experimental value. So to conclude this presentation, I would like to just to briefly mention an extended in situ test campaign in which we as University of Pavia were involved in recent years. Now the problem was the problem of the seismicity induced by the gas extraction in the northern part of the Netherlands. Now I think there will be a webinar dedicated on this topic, but here I will briefly mention the problem. What happened was that in this area of the Netherlands, the building stock was mainly made by unreinforced masonry buildings, which have not been designed to withstand earthquakes, because natural seismicity is not an issue in that area. But a series of earthquakes happened due to these gas extractions. Luckily, the magnitude was quite reduced, but these buildings were somehow vulnerable to this seismicity. So there has been a huge project dedicated to the study of this vulnerability, the vulnerability of these buildings. This project was consisted also of a large experimental test campaign, included both laboratory tests, also both on components, but also on entire buildings. But also it included also some numerical simulation using, among the other software, also the software Tremori, and it included also a quite large in situ experimental test campaign. Here you can see some of the buildings that were tested. Now, let's say the new aspect of this test campaign was the fact that we were able to obtain a large number of results. because usually you're not performing a wide number of tests when you're doing an in-situ test campaign. And this information allows also us to possibly have information regarding the correlation among the mechanical parameters inside a building, also with respect to the total buildings that were tested. So with this, I think I have concluded my presentation. I have said more or less everything that I wanted to say. I want to thank you for your attention.